the net change theorem, and the indefinite integral. Today's objectives: we're going to apply the net change theorem to topics involving science, engineering, and other disciplines. We're going to evaluate indefinite integrals to gain a family of antiderivatives using the notation of the elongated s. We're also going to evaluate definite integrals for a finite number. Our first few examples are going to piggyback off of the Fundamental Theorem of Calculus. For the first 5 examples, we're going to use the Fundamental Theorem of Calculus to interpret the scenario. The first example talks about an object that moves along a straight line, and it has a position function s of t measured in meters. Then the velocity is actually the derivative of s of t, measured in meters per second. What does this definite integral represent? There's many ways to try to interpret this, but the first method I'm going to use is actually a very scientific method called unit analysis. What I'm going to do is actually multiply v of t times dt. But we're just going to indicate the units. So the units for velocity is meters per second, and dt is measured in seconds. And if you look at this very, very carefully, you're going to realize the units that are left are actually meters. And what are meters representing? Meters is representing the position of the object. Another way to interpret this is simply rewrite this definite integral and substitute what you know. We know the velocity function is the derivative of the position function. Now, by the Fundamental Theorem of Calculus, this must be the net change of the position on the interval from t1 to t2. Let's look at a different scenario. The marginal revenue function, derivative of capital R of x, is measured in dollars per unit. This is obviously the derivative of the revenue function, capital R of x, where x is the number of units sold. What does this definite integral represent? Once again, we could actually multiply the units that represent the derivative of R of x times d of x. This is dollars per unit, and dx is measured in unit or units. Notice the units reduce, and you're just left with dollars. Now the dollars must represent what? The dollars are the units for the revenue function, which gives us the hint to interpret this definite integral from 75 to 150 units. This must be the net change of the revenue from 75 units sold to 150 units sold. What does the definite integral represent in the next example? Once again, we could do unit analysis. We have pounds per year multiplied by year. We're left with pounds, and pounds must be a measurement of the weight of the whale. You might be noticing a pattern. And that pattern includes the word net change. We could do a similar analysis for the next example. And this next example talks about the mosquito population. The only difference is that you're starting with 25 mosquitoes. Even if you're not familiar with electricity and currents in a wire, we could still analyze the next definite integral. we have a definite integral, and we could substitute the function I of t with the derivative of q of t. And by the fundamental theorem of calculus, this must represent q evaluated at b minus q evaluated at a. Which is the net change of charge from A to B. This brings us to a refinement of the fundamental theorem of calculus. However, please do not fall in love with all the symbols and patterns. Make sure you understand the vocabulary from the scenario and look at the units being measured. The net change theorem. The definite integral of a rate of change is the net change and is evaluated by this definite integral. Keep in mind this is a refinement of the fundamental theorem of calculus. We'll look at an example where the capital letters really do not matter that much. Instead, you got to pay attention to the vocabulary. My hint to you is to look for the rate of change and write down those units. So in this first example, the rate of change is specified by liters per minute. So if you write liters per minute, and the idea is to later multiply this by minute, we now have a better hint on how to rewrite the scenario as a definite integral. Now we need the total amount of water from the tank during the first 10 minutes. So this time our domain is from 0 to 10. Our rate of change is actually r of t, and we want to multiply this by a very small interval of time called dt. Now we simply substitute and use your knowledge of antiderivatives to evaluate this definite integral. We're going to evaluate this from 0 to 10, which is represented by the net change. Notice with polynomials, sometimes the evaluation is much easier. And notice our units end in liters, as expected. Make sure you could write a short conclusion to any of these scenarios. Let's look at another example where you have to analyze the units of measure. Make sure you're looking for that first instantaneous rate of change. A bacteria population is 4,000 at the time of 0, and the rate of the bacteria growth is given as the product of two functions. This rate of bacteria growth is measured in bacteria per hour. What is the population after 1 hour? My first search is to look for this rate of change, which is measured in bacteria per hour. I'm going to write that down. Bacteria per hour. And if I take that and multiply this by a small interval measured in hours, our units will change. It will actually change into bacteria. Now, bacteria per hour is representing the rate of bacteria growth. The rate of bacteria growth is indicated by these symbols. And then we need to multiply this by a small increment of time, which is what we call dt. Now we're ready to translate this scenario. There is an initial population of 4,000. And we want to know how much bacteria is added on after 1 hour. So we need a definite integral with the domain from 0 to 1. And what are we adding up? We're adding up the rate of change multiplied by a small increment of time. So we're going to add 1,000 times 3 to the t times a small increment of time, which is dt. Use your knowledge of antiderivatives to simplify this. And we need to find the net change after 1 hour. Make sure you know your log properties. We have the ln of 9 plus 1 all over the ln of 3. And that is measured in bacteria. Make sure you could approximate this on a scientific calculator. It's approximately 5,820 bacteria. The population after 1 hour is about 5,820 bacteria.